We begin our study of precalculus by looking at functions. First, however, let's look at what a relation is. So a relation is a set of ordered pairs, x comma y. The set of the first components is called the domain, and the set of the second components is called the range. Each value in the domain is known as an input value, or an independent variable, whereas each value in the range is known as an output value, or a dependent variable. So we consider the relation, that is the set of the ordered pairs 1, 2, 2, 4, 3, 6, 4, 8, and 5, 10. The domain of this relation is the set 1 through 5. The input values are 1, 2, 3, 4, and 5. The range is the set 2, 4, 6, 8, 10, and the output values are 2, 4, 6, 8, and 10. We can now look at a function. A function is a relation in which each possible input value leads to exactly one output value. We say the output is a function of the input. So the input values make up the domain of the function. The output values make up the range of the function. So let's look at this. So we have the inputs P, Q, R. We have outputs M and N. Let's see. P outputs to M, Q outputs to N, and R outputs to N. Each input goes to only one output, and so this is a function. We now look at the set inputs P, Q, R, the set of outputs X, Y, and Z. P goes to X, Q goes to Y, R goes to Z, and each input only goes to one output, and so this too is a function. Look at this one and we go, okay, well, P goes to X, Q goes to Y, but Q also goes to Z. Uh-oh. Q goes to two different outputs, so this cannot be a function. So, to summarize, both A and B represent functions, whereas C does not. We typically represent a function by y equals f of x. The function name is f, and I already said it, it's read y equals f of x, or y is a function of x. X represents the independent variable, and y represents the dependent variable. So now consider the function f of x equals x squared plus 3x minus 4. We wish to evaluate these four. F of 2, f of a plus h, and then f of a plus h minus f of a all over h. So first start with f of 2. To evaluate a function at a given point for a given value, what we're going to do is everywhere we see an x, we're going to replace it with a 2. So we'll have 2 squared plus 3 times 2 minus 4. So this is 4 plus 6 minus 4. This is 6. So f of 2 is 6. Well, now for f of 8, same idea. Everywhere we see an x, we're going to put an a. So we get a squared plus 3a minus 4. And there's no other way for us to simplify that. So for C, f of a plus h, so we get a plus h squared plus 3 times a plus h minus 4. Now a plus h squared, you should remember from algebra that the quantity of a plus b squared is a squared plus 2ab plus b squared. So using that, a plus h squared is a squared plus 2ah plus h squared. Then we have plus 3a plus 3h and minus 4. And we can just put it in that form. So now for the last part. Well, we just found f of a plus h. That was a squared plus 2ah plus h squared plus 3a plus 3h minus 4. We also already found f of a, that was a squared plus 3a minus 4. Now that whole thing is going to be divided by h. Well, we have an a squared here, and we have a minus a squared, so they're going to drop out. We have a plus 3a, we have a minus 3a, they're going to drop out. Then we have a minus 4 and a minus minus 4, so they drop out. So what we're left with is 2ah plus h squared plus 3h all over h. If you notice, there's an h common in the numerator, so we can factor that out, and we're left with a 2a plus h plus 3. And now those h's can drop out, and we're left with 2a plus h plus 3. By the way, this value is called the difference quotient of f at a. Now we're given the function h of p equals p squared plus 2p. We want to solve h of p equals 3 for p. So if h of p equals 3, this means that p squared plus 2p is equal to 3. And you should remember from algebra that to solve a quadratic, we want to set it equal to 0. So this is p squared plus 2p minus 3 is equal to 0. Now we can go one of two ways. We can either factor, if it's possible, or we can use the quadratic formula, which says if you have ax squared plus bx plus c is equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, p squared plus 2p minus 3 can be factored, right? Because we're looking for factors of 3. When subtracted, give you 2. Well, 3 minus 1 is 2. So there's going to be a P in each grouping. You want 1 and 3. The higher will take the positive. So this factors the P minus 1 times P plus 3 is equal to 0. Then remember, we can use the zero property, which says if A times B is equal to 0, then either A equals 0 or B equals 0. So this means that P minus 1 is equal to 0, or P plus 3 is equal to 0, which means that P is 1 or P is negative 3. So our solution for P is the set negative 3, 1. Now let's take a look at these. Let's express, if possible, the relationship as a function of the given form. So look at the first one. We want to express the relationship 2n plus 6p equals 12 as p being a function of n. In other words, what we want to do is we want to try and solve this relationship for p. Well, the first thing we would do is subtract both sides by 2n. So we're left with 6p is equal to 12 minus 2n. We would then divide both sides by 6, so we'll have p is equal to 12 minus 2n all over 6, which we can simplify as 2 minus n over 3. So f of n is 2 minus n over 3. Now we want to try and do the same thing for the relationship x squared plus y squared is equal to 1. We want to try and express that as a function of x. So x squared plus y squared is equal to 1. Well, the first thing we wanted is subtract both sides by x squared, so we'll have y squared is equal to 1 minus x squared. We take the square root of both sides, so y is equal to the square root 1 minus x squared. However, remember, when you take square root, it's either positive or negative. So we have y is equal to plus or minus square root of 1 minus x squared. Well, it is impossible to express y as a function of x because there are two possibilities. For y, we have y is either the square root of 1 minus x squared, or y is negative square root 1 minus x squared. So what this says is that x, any input value of x, maps to two different outputs of y, which we know is not a function. So let's take a look at this graph. So this figure tracks the value of an initial investment of $100 in the S&P 500 from 1970 to 2010. Now we can see that the investment was worth $1,000 5 times during this period. Right, so here's 1,000. So Let's just trace. There's once. Come down. That's probably about 1997 or 1998. Come back over. Well, there's another one. This was probably about 2002, 2003. That's probably 2004, so this one's probably 2002. So that's 3 times. Okay, here's a fourth. That's probably about 2008. And then here, that's looks like 2010. Now, notice that this is not a violation of the definition of a function, right? Because each year, if you look at the graph, each year corresponds to just one value of the investment. There is a special type of function in which each output has one and only one associated input. This is known as a one-to-one function. So a one-to-one function is a function in which each output value corresponds to exactly one input value. That is, a function f of x is said to be one-to-one whenever f of x sub 1 equals f of x sub 2 implies that x sub 1 equals x sub 2. So there are 2 ways to determine whether a function is one-to-one. We have algebraically and we have graphically. The graphical method is known as the horizontal line test, which states that a function is one-to-one if and only if any imaginary horizontal line crosses the graph function at most one time. So we go back real quick to this graph of the S&P. We can draw any horizontal line. That's fine, but right here we already showed that at 1000, that horizontal line crosses the graph 5 times. So this fails the horizontal line test. We're going to look at the algebraic technique here. Is the area of a circle a function of the circle's radius? If it is it one-to-one? So, recall from geometry that the area of a circle is given as pi times the square of its radius. Now, this is clearly a function of r, right? Each value of r goes to only one area. So we could write it as a of r. Now we need to determine if it's one-to-one. So let's suppose that a of r1 is equal to a of r2. So this would mean that pi r sub 1 squared is equal to pi r sub 2 squared. Well, there's a pi on each side, so we can divide by it. This would mean that r sub 1 squared is equal to r sub 2 squared. Now, if we take the square root of both sides, we'll wind up with the absolute value of r sub 1 is equal to the absolute value of r sub 2. Now, can the radius of a circle be a negative value? Well, no, right? Technically speaking, a circle of radius 0 would be a point. We typically exclude that case. So we have the restriction that r is between 0 and infinity. Again, theoretically, a circle can have an infinite radius. So using that fact, we have that R1 is indeed equal to R2. And so therefore, A of R is 1 to 1. So the area of a circle is indeed 1 to 1. Which means that the area of a circle is unique according to its radius. So two circles of different radii cannot possibly have the same area. We conclude this lesson by looking at what's known as the toolkit functions. So we have what's known as the constant function, which is simply f of x equals c, where c is a constant. Its graph is a horizontal line. Notice that this is not 1 to 1, right? It fails the horizontal line test. The next is the identity function, which is f of x equals x. This is just the straight diagonal line that goes through the origin that has slope 1. Now this is 1 to 1. We have the absolute value function, f of x is equal to the absolute value of x. The result is a v with the vertex at the origin. This is not 1 to 1, right? It's a horizontal line test. Next, we have the quadratic, f of x equals x squared. This shape is a parabola, and it's not 1 to 1. We then have the cubic, f of x equals x cubed, which results in this sort of almost an S shaped thing. Kind of looks like a sideways S. And this is 1 to 1. We have the reciprocal function, which is f of x equals 1 over x. It results in two parabolic shapes. And this is 1 to 1. We then have the reciprocal squared, so 1 over x squared results in this looking kind of graph, which is not 1 to 1. We have the square root, f of x is the square root of x, which is sort of like a half sideways parabola. This is 1 to 1. And finally, we have the cube root, f of x equals the cube root of x, which again is this curvy S kind of thing. And this is also 1 to 1. Now, the toolkit function will be used a little bit later when we start looking at transformations of functions. However, that concludes this lesson on functions.